So this proof combines a couple of insights, one from Oresme and then one from Leonhard Euler. And the way it works is to, first of all, take the harmonic series as a sum, going 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, etc. And then to re-express that as a product, where these terms keep multiplying together. Where we're going through the prime numbers continuously. And it's to work out that these are actually equal to each other. And that part was done by Leonhard Euler. So with these primes being 2, and then 3, and then 5, etc. So the significance of this going to infinity, and therefore, because these are equal, because this is just a re-expression of this thing going to infinity, to positive infinity, is that for that to be the case, where we have these finite terms all multiplying each other, for these to actually get to positive infinity, there has to be an infinite number of them. And because they're all the next prime along in a series of primes, then it's necessary for there to exist an infinite number of primes to satisfy that demand, which makes this go to positive infinity, and which therefore makes this true, after we've already established that this is true, that this equivalence between these is true. I'll do the slightly less complicated bit, which is showing that these numbers all added together go to infinity. And then the second slightly more complicated part is I'll show how you go from this to this. So I'll just draw a few more terms into this sum. And one thing that we can do that'll show that all of these, as we keep going, make something that just gets larger and larger and larger, is that we can actually round some of these terms down. So for example, make this a quarter, make this an eighth, make that an eighth as well. Make this one a 16th. And we notice that we can keep doing this in such a way that now with this sum that's going to a lower value, we're consistently getting, after the first term, a half, plus a half, plus 4/8, that's a half, plus 8/16, that's a half, and that this just keeps on going forever and ever and ever. So we now know that there's an infinite sum that's smaller than the infinite sum, we were looking to see if it would go to positive infinity. We can see that this smaller one actually goes to positive infinity because it's 1 plus a half plus a half plus a half plus a half just forever. So it just keeps getting bigger and bigger and bigger. Or since we've noticed that it has the form half plus half plus half, you group these halves together and notice that it's actually 1 plus 1 plus 1 plus 1 plus 1 forever. And because of that, because we know that this goes to positive infinity, we know that this, which goes bigger even faster, must necessarily go to positive infinity. Okay. So the way that we convert this to this is quite a long process, and I guess the best way to show you how it's done is just to do it. However, I'm going to need to write this a lot, so I'm just going to use Z as shorthand for this. So just use 8 terms because otherwise doing this is going to take an enormous amount of time. And just remembering that I'm relabeling this whole thing as Z for the sake of brevity. So the first thing that we're going to do is make half Z. So that's just going to be all of this times a half. And then the next thing I'm going to do is I'm going to subtract all of this from this. So I'm going to have Z minus a half Z. And if you notice, all of these terms where the bottom is a multiple of 2 will be able to cross off. So we're just going to be left with 1 on 1, 1 on 3, 1 on 5, 1 on 7, 1 on 9, 1 on 11, etc. And we can't see it yet, but what this is starting to do is basically 2 is a prime number. We're pulling out all of the multiples of 2 on the bottom of this fraction. And then we can also rewrite what we have here as being 1 minus a half Z. So that's what this is. Now, a basic idea is we're just going to repeat this pattern with 3 and 5, so the next couple of prime numbers, until it's obvious what's happening here. So, if we want to take a fifth of 1 minus a half Z, we start with 1 on 5, because we're multiplying all of these by a fifth. 1 on 15, 1 on 25, 1 on 35, 1 on 45, etc. And then, if we want to subtract a fifth of 1 minus a half z from 1 minus a half z, then we just take this away from this. And we notice a similar thing that happened to how we were able to re-express this as this. Where we have 1 minus a fifth z times 1 minus a half, or we can express that by just putting the z over here. And then we repeat the process as well. Now I accidentally skipped to 5 rather than 3, but slightly running out of space. I'll do it up here if I can. Okay, so if we want to take a third of 1 minus a fifth times 1 minus a half z, then we already have 1 minus a fifth, 1 minus a half z, which is all this. So we're just going to multiply all of these by 3. 1 over 9, 1 over 21, 1 over 27, 1 over 33, 1 over 39. And then if we want to subtract this from this, which is going to be 1 minus a third, 1 minus a half, 1 minus a fifth z. And you can see that as we go along this process, we're actually stripping out from our original sum, which was this, all of the multiples of prime numbers. And if we strip out all of the multiples of prime numbers, we eventually end up with nothing other than this. That's a z. And we end up with this. With, of course, all of these continuing. So if we want to work out what z is in terms of all this stuff, you know, with these continuing going on, with this, and this, more and more primes, then all we have to do is divide both sides by z and then flip everything over, because we're able to flip fractions and we can implicitly see all this as being over 1. So what happens when we do that? When we invert and times by 1 on z is we get this equaling z, which, if we remember, was this. Now this whole thing, so all these multiplying each other, could also be split up, and it could be re-represented as 1 over 1 minus a half times 1 over 1 minus 3, 1 over 1 minus 5, etc. Which can be a little more neatly expressed just as this, which is what we had at the start. And if you remember the scheme of the proof, this is equal to this. This goes to positive infinity, which means that this has to go to positive infinity. This is comprised of finite numbers multiplying each other. So it means that we can't ever stop putting on another number. We have to keep putting on more and more and more, multiplying by another number and another number and another number for this to ever be able to get up toward positive infinity. And because of that, because each of these that we make requires a new prime number, there therefore has to be an infinite number of prime numbers.